Okay, hello everyone, welcome to the live stream. And this is the first time I'm streaming a lesson live. And the topic which I have chosen for today is the topic of relativity, rather specifically special relativity. Okay, so special relativity. So this is what I'm going to start with, and I intend to carry out such live streaming sessions regularly, and hopefully after my intended period of time, I'll have a complete version of playlists containing all the live streaming on special relativity. In fact, if I can keep going in future, I'll probably encapsulate a lot of topics in general relativity as well, but that's a far-fetched idea. I just want to test the live streaming starting today, and if possible I want to see how far I can go with this. Alright, so that's my goal. So I'll take this as a test. You can show me your support by subscribing to this live stream, or asking me a question, or I'll save these videos for you as well, so you can ask questions in those as well, and then I can address them specifically in future videos or future sessions. So without further ado, let us start talking about special relativity. Specifically, I'm going to start with the structure of the space-time of relativity. So what we'll start with our discussion is basically typically where we start our discussion on special relativity with, and that is the idea of something called an inertial frame. Okay, so we have Newtonian or relativity in the Newtonian world, so it's not like the special relativity is where we start to talk about relativity. That's not true. We usually talk about relativity in Newtonian mechanics as well. Specifically, it's called Galilean relativity. Okay, so if I have to give you sort of background, there are two types of relativity we'll be talking about. So relativity, if I want to talk about relativity, it has two types. One is Galilean, okay, and the other type of relativity is Einsteinian or Minkowskian. Okay, Minkowskian. Okay, so it's the Minkowskian relativity that is usually known as the special relativity. So what is going to happen is that in either case, we'll notice that in whatever situation you are in Newtonian mechanics or in relativistic mechanics, wherever you are in, everything is functions of space and time. So any physical quantity, usually any physical quantity, or I should say not physical quantity, or any physical event, something called event, it depends, it is described with four numbers, okay, or location, Location is sort of a special thing, right? But event is more useful. Okay, so let's talk about event. Requires 4 numbers, right? 4 numbers. So basically we need 3 numbers to describe where it is. There's the special location, but there is also the question of location in time, right? When did it happen? That's also an important thing. So we talk about time as well. So time, okay, and then 3 numbers to specify special position. We call them coordinates. So t, x, y, and z. Okay, and usually quantities depend on these 4 numbers. So, and these are the spatial coordinate as the time coordinate, time coordinate, right? And also usually physical quantities or measurements depend on these 4 numbers. So quantities can depend on these 4 numbers. So which kind of quantities? For example, like electric field, magnetic field, temperature could be. So quantities, example would be electric field, okay, or magnetic field. We write it with B, magnetic field. Or for example, these are vector fields, but I can also go for scalar fields like temperature, temperature field, T, temperature. That also depends on where you are, in what is the location, but also temperature can change with time, okay, and so on and so forth. So things that we can measure usually comes from these 4 numbers, these 4 coordinates. And so you notice these coordinates are different. So one is time. Time is, in our mind, if you think in terms of Newtonian mechanics, is sort of independent of the space, and space is independent of time. Okay. So in some sense, the first one is a bit different, usually from our experience, and the last 3 are also independently chosen, but they're arbitrary, right? So we have sort of divided into 2 groups. As a foreshadow, I'll have to warn you that eventually we'll rescind this discrepation, this difference or discrepancy between these 2 groups. But nonetheless, for now, I'm just talking about our experience or thinking pattern that we have inherited from studying the Newtonian mechanics, is that these are 2 different sort of things. A lot of the time we'll put a semicolon in here, right? But let's not overcomplicate things. And these 4 numbers, these 4 quantities, or scales of these 4 quantities, create something called a frame. Okay, so what's a frame? As we are hearing a lot about this, and since we'll be talking about inertial frame, it's very important to talk about frames. So our topic at hand is inertial frame, and relativity. Let me check if there is any question from anyone. No. Okay. So, anywho, let's keep going. Okay. So, an inertial frame is basically the scales of these four numbers. So, let's say we are in three-dimensional space, with Euclidean geometry. Soon we'll be talking about what that means as well. But essentially, what we have in space is we can establish what we call the Cartesian coordinate, orthogonal Cartesian coordinate, where we have these coordinate patches, right? The coordinate axis. So one in this direction, one in this direction, and another one in, let's say, start from here, this direction, right? And let me change the colors to black. I think that would be far more appropriate. Okay, and then, so what do? We say, okay, this is, let's say, x-axis. Okay, so this is the x-axis. I'm sorry, so this is the x-axis. This is the y-axis. This is the z-axis. Usually, typically, we take a right-handed system. That's what I have chosen in here. And then there is a clock. So let me just make all of this black for good reason. Okay, and then we have a clock attached at the origin. Okay, so let me just draw it in here. So there is a clock. Okay, the clock is basically a stopwatch, or it's just an independently running clock. And this is what we call an inertial frame. There's an origin. We call the origin O. The clock shows the time t. Okay, so the combination of this, there's these three axes, which are basically the scales. And there's also a time scale, right? So these are all scales. There are markings. So this is 1, this is 2, this is 3, this is 4. This is the coordinate units, and we choose the similar units in all axes, presumably of similar length, although we haven't specified what length is. But inherently, these axes are identical for our own purpose, and so we have 1, 2, 3, 4 as well. So this is our frame. This is our frame of reference. Okay, a frame of reference which has an origin O, which has which produces 4 numbers. So frame of reference, what is that? This is 3 special basically scales or axis or scales, okay, and a clock. And we call this frame S. This is a name. We call it as S. Okay, so now what we can do is any point in terms of these numbers, so let's say this is a point, this will have a location in space. Okay, and so you use 3 numbers. So let's say, how do you take the 3 numbers? You drop a perpendicular on the x-axis. Actually, you draw a perpendicular parallel to the y-axis, and then from that point you draw you draw a parallel line, a line parallel to the y-axis, intersects the xz plane, and then from that point, right, you draw another parallel line parallel to the z-axis, which will intersect the x-axis here, and then one you draw in parallel with x-axis, which will intersect the z-axis here. Okay, and then if you notice, from the origin, you can draw a line to this shadow point, and that line will be entirely contained in the zx plane, and then you can draw a parallel line parallel to that line, which will eventually intersect the y-axis at some point. So you have this is the x coordinate reading, this is the z coordinate reading, this is the y coordinate reading, and then there is a question of time, and this will clarify what we mean by event. The idea of event is basically something is happening at a location. So that essentially means that something also happened at a time, right? For example, there's a flash going up, something was crossing this line at certain point. So for example, this could have been a trajectory of something, and at a given time that object was at this location. So this justifies the use of 4 numbers, okay? Basically 3 numbers to designate the position or the location in space, and 1 in order to specify the time. Okay? Now, you have to understand that this frame is not unique. This is sort of arbitrary. For example, one thing that can be said is that x and y didn't need to be perpendicular on each other. Neither needed the z. We could have chosen the origin anywhere. Okay? There's a lot of things at stake here, a lot of things that are arbitrary. And indeed, the scale that we use to measure the distance, the points we have, or the measurements we have in the scale, that's also arbitrary. There's a lot of arbitrariness in here, that is true, but and also the frame itself can move, right? For example, this O point, think about this as a solid, rigid frame, right, made up of wood or bamboos, and you can translate it, you can rotate it, you can take it anywhere you want. So that means technically this frame itself could move. And if you can think of this frame being attached to an observer, then observer can move, the frame can move. So basically, when we say something is a frame or from some frame, we essentially means it is attached to some kind of observer. Okay, that's what we mean. And there can be other observers, so therefore there can be other frames we can construct. Now we come to the physics of it. Okay, so these are the scales. There is a lot of arbitrariness associated with the scales. So then the question is, where's the physics? Are we defining only arbitrary stuff, or are we going to do some sort of physics? And this is where the physics comes in. What we want to do is basically talk about acceleration. So think about acceleration. So what is acceleration? Acceleration is basically the derivative. So we denote it by a, and a is a vector. Don't worry, I'll hardly use vectors in here. In the subsequent stages, when we'll be relying heavily on vectors, especially basis vectors and all this stuff, and the changes, I'll be discussing them in details before using them right away. I'm assuming that if you're watching this during the live stream or any point afterwards, you are somewhat familiar with vectors and Newtonian mechanics, so from that assumption, I'm discussing the fact that the acceleration is the derivative, is the time derivative of velocity. We all know that, and in turn, velocity is the time derivative of position of an object. So basically, I have the time derivative of our time derivative, and that takes us to a double derivative, so d2r dt2. Okay, now all know that this r vector, the position vector, which can be a function of, which is essentially a function of time, not just can be, is basically written as follows: x as a function of t, and then we have x hat to indicate Cartesian unit basis vector, plus y, which is also a function of t, and then y hat, again unit basis vector. These are also constant vectors, they do not change, they do not depend on time, so all the time dependence essentially comes from the coefficients, right? And then you have the z-axis, z of t, z hat. And so if you take the derivative, because x hat, y hat, and z hat are essentially constants, if you take the double derivative here, d2r dt2, which is basically the acceleration. Let me just suppress the time dependence for a second. So the time dependence is there, I'm just not showing it explicitly. What do I have? I have the second order time derivative of x times x hat, plus similarly second order time derivative of y, and then y hat, and then plus d2z dt2 z hat. So why I'm talking about acceleration? I'm talking about acceleration because if you're in a car and the car is moving at a constant velocity, what we can observe is that sometimes it is very difficult for us to say that we are moving physically by making experiments inside the car or inside the train which is moving at a constant speed. It is indeed difficult to know whether we are moving or not, especially if you do not look outside. If there is a window you're looking at outside, then of course everything is going behind, you're at your own state. But I want to invoke an experiment where, think of two trains that are moving side by side with constant speed, and the speeds of each of the trains are equal to the other. Think of that situation. Now if you look from one train to the other, as there is also a passenger right where you're looking at, the passenger is moving and you're not moving with respect to the passenger. It sometimes it feels like that you're not moving at all, right? If you really focus on the train, focus on the other train, or think about someone who is sitting in your own train. With respect to them, you're not moving. So then you try to make an experiment, right? You try to make an experiment. So this is you inside a train. So let's say we draw a picture. So this is you, right? So, just a portion of the train, okay? And this is the floor. This is where you're sitting down, okay? So this is your table, this is your chair, and this is you sitting there. Okay, so you try to make an experiment to ensure that to try to understand if you're moving. I can guarantee you that if there is no change in velocity, then no matter what kind of experiment you make, you won't be able to understand whether you're moving or not. Okay? Because in some sense, constant velocity, constant velocity, not just velocity, constant velocity. I didn't say speed because the train could be going in a circle, and in that case the velocity is not constant, okay, even though the speed could be constant. What I'm talking about, constant velocity. If the velocity is constant, then you cannot make any experiment to distinguish between your current velocity or in a different constant velocity. That's very important for us to understand, okay? So in our frame, you can think of a train when we're talking about frame. Okay, let's a train. Okay, in a train, you cannot conduct an experiment. To determine its velocity if the frame is not accelerating. So basically, you going on 20 mile per hour or 30 mile per hour, there is no way you can differentiate between them. Okay, if you do not have, for example, of course you can look outside, but let's say there is nothing outside that gives that away, or there is no, you cannot look outside. Okay, there is no window. Okay, you're purely within the train. The train is moving at constant velocity. There's no acceleration. Then you cannot determine what the velocity is. Okay, or even if there is a velocity. Okay, so that means that there is a class of frames. There is a category of frames. As long as they are not accelerating, then it doesn't matter which frame you are. The physics looks the same. Okay. And how do we know that? We know that from the fact, by guaranteeing the fact that the train is not accelerating. What happens if there is an acceleration? So let's say there is a pendulum, right? So from the ceiling, there is a pendulum. The pendulum will hang straight and will not move as long as you're moving at a constant velocity. But if you change your velocity, if you suddenly accelerate, then it will start to swing to one side. And then if the acceleration stops or acceleration changes, it will swing accordingly. Okay, and in weird fashion, and that will tell you that there is an acceleration in the frame. Okay, so acceleration is something that every moving observer agrees on. So acceleration can be detected. Not only that, you can create an experiment which measures the acceleration and be measured. So since zero acceleration cannot be distinguished, especially if you're thinking about in terms of different frames, and all of them have no acceleration, then there is no way to know whether you are moving or someone else is moving. There's no way to tell, right? Two trains moving side by side. Let's say you are in a train, you look outside, there is another train moving on an adjacent slot, going this direction. Okay, from your point of view, you are here. From your point of view, the other train is moving in the opposite direction. It could be that that train itself is stationary and you are moving in the forward direction. According to observation, according to physics, there's no notable difference between these two scenarios. Okay, the only thing we can agree on is that there are relative motion. So without acceleration, without acceleration, motion, non-zero velocity, and zero velocity cannot be differentiated. Zero velocity and non-zero velocity in your own frame cannot be differentiated in own frame. You cannot distinguish between the two scenarios. Okay. Number two, if you look at another frame for two non-accelerating frame, only relative motion, that is, you're moving with respect to one another, but you're not absolutely sure who is moving, or both can be moving in such a way so that they both agree on the same relative motion. But that situation can occur in infinitely many different ways. Okay, so for example, you're noticing that the other train is moving in the opposite direction at 5 meters per second. So you say, okay, the relative velocity is minus 5 meters per second. But then that can be realized in a lot of ways. For example, you can move in this direction by 1 meter per second, and the other train can move in the opposite direction at 4 meters per second. Okay, you'll say minus 4 meters per second, and then that creates negative 5 meters per second of relative motion. Okay, so only relative motion is agreed upon. So that means if there is no acceleration, then there is a special class of frames. Okay, and that is what we call inertial frame. So hence we have this definition. What is the definition? The definition is there exists a class of preferred non-accelerating frames, right? Non-accelerating reference frames or systems. And this is the important part, because it's non-accelerating. This is where Newton's first law holds. So this is a class of preferred non-accelerating reference frames where Newton's first law holds. So such systems or such frames are called inertial frames. Inertial frames. Let me write that in uppercase letters. So inertial frames. Okay, so that means what? The acceleration is 0. So acceleration is 0. That is the condition for the frame itself. Or equivalently, you can say in Cartesian coordinates, d2x dt2 equals d2y dt2, second order derivative of y with respect to time, second order derivative of z with respect to time, all are equal, and they are all equal to 0. Why? Because the acceleration is 0, and acceleration is a vector, and if the vector has to be 0, all the components will have to be 0. That's why each of them are individually 0. Okay, and so therefore we can conclude, therefore if there is no gravity, without gravity, if we have two inertial frames, two inertial frames, let us call S and S prime, can only differ from each other by one, a translation, two, a rotation, or so these are all alternative, right? Translation, or actually both can be exist, so and or a rotation and or something called a boost, so a motion of one frame, a motion of one frame with respect to the other at a constant velocity. Right, so one is being translated, that means separated by some distance, and both are moving at same velocity, or one is a bit rotated, one is a bit tilted, but still they're moving in the same direction, and or one is moving in a different speed but constant speed with respect to other, that is they have relative motion, relative constant speed. Okay, so there is only this three distinction between the two inertial frames. Okay, there can be no other. Okay, as long as there is no acceleration, the two frames are inertial and they are related. They have these three differences. They're the same in all the other aspects. Okay, and this is how we have built what we call the inertial frame, or in more rigid terms, inertial reference frames. And why do we need them? Inertial reference frame is very important for the principle of relativity. So the question is, why do we need inertial reference frame. So why do we need initial reference frame? Because it is central or fundamental it is central or fundamental to the principle of relativity. Okay, and what is the principle of relativity? What is that? So let me write that here as well. We'll state that and probably end our session here. So the principle of relativity is simple. Let me use a different color. It basically says the laws of physics. So let me just principle of relativity. So it says the laws of physics take the same form in every inertial frame. That is the statement. The laws of physics take the same form, emphasis on the form, okay, in every inertial frame. I know we're not talking about like the coordinate form or something like that, like in full-fledged geometric form or vector form, where we're not mentioning coordinates, but this is the form is basically coordinate independent statement. Coordinate independent statement. Okay, so for example, if in your frame you have like a law F equal to ma, in let me just write it down for you. So for example, in one frame you have F equals ma, and in another frame you'll have F prime equals m prime a prime. The form is going to be invariant. This is also called covariance, but we'll be talking about that in details in the next day. So this is where I'm going to stop today's live stream, and then on the next class, probably next session, I'm going to explain that further. So having said that, I'm gonna finish it here, okay, and hopefully I'll see you in the next stream. So most likely you'll be looking at this after the stream has ended, don't worry. The stream will be around this time, or you can tell me a preferred time, then I can probably try to stream then, okay. If you have watched it for some seconds